Thank you all for coming today and for having me for the lecture today. I want to try and explain to you a little bit about dark matter today. So dark matter is a substance that we think makes up most of the mass of the universe. It appears to be completely invisible, and we only seem to know about it through its gravitational influence. And if that sounds completely crazy, my one objective today is for you to not think that I'm totally mad by the time you leave this room. And a little bit more than that, I'd like at the end of the talk, if I can, to get onto some of my own work on the subject, some recent work where we think we've uncovered evidence that dark matter can be moved around at the center of galaxies as they form. And this is giving us new clues as to what dark matter might actually be. But let me start with a little bit of history. So what is the historic evidence, the reasons why we started to believe as a community that this dark matter might be out there? Well, some of the earliest and most compelling evidence came from the rotation of stars and gas in galaxies like this one. This is the beautiful Andromeda spiral galaxy. It's the nearest large spiral galaxy to us, and if you have a decent pair of binoculars and can get out of the city, you can actually see this with your own two eyes in the northern hemisphere. And this was being studied by Vera Rubin and others to try and work out how fast it's spinning from its center to its edge. And this is a way of measuring the gravitational field in this system, because the faster it's spinning, the stronger the gravitational force must be to hold the system in equilibrium. So you can imagine building a plot of the velocity of this galaxy, so how fast it's spinning, versus distance from its center. And when Vera Rubin and others like Ford looked at this galaxy, what they expected to see is something like this blue line. And what you see here is as you go to the center of the galaxy, there's very little enclosed mass, so the velocities are very low. And then as you move out here, there's more and more and more closed mass, so the velocity rises because the gravitational force is getting stronger and stronger. But then at some point, you're not adding any more stars anymore, you're just getting further and further away from this object, so the gravitational field strength starts to fall again, and you expect the velocities to come down like this towards zero. And in fact, this is exactly what the planets in our own solar system do. If you measure the rotation speeds of planets in the solar system all the way out to Pluto, which is a dwarf planet now, but all the way out to there, you see the velocities gradually coming down just like this. But of course, this is not what Vera Rubin saw. Instead, the velocities seem to remain high all the way out here, where there's no visible stars or gas anymore. And that was quite a surprise. And it's not just for Andromeda that you see this, but you see this kind of effect for every single rotating disk galaxy that we have studied to date. And what it seems to be telling us is that the gravitational force is much stronger out here than you would expect. And one interpretation of that is that there's an awful lot more mass out here than we can see.
Speed or just speed?
This is the rotational speed.
Angular speed.
Angular speed,
Okay.
exactly, yeah. The galaxy is spinning. So one interpretation is that there's missing mass out here, but if there is, we've looked across the whole electromagnetic spectrum, and we can't see that material in absorption or emission of light, so it must be invisible, which is a pretty startling claim. So one should consider other things, right? It's possible that there's just an observational error, a mistake. It's possible that the system is not in equilibrium. Maybe it's about to tear itself apart. Now, we've done a lot of work over the last 30 years or more testing these two ideas, and we're pretty confident that it's not an observational error. We've looked again with ever-improved instrumentation, two-dimensional velocity field data, and so on, and the result just will not go away. And the falling apart thing seems unlikely because we see this in every single galaxy, so you'd need every disk galaxy in the universe to be on the cusp of falling to pieces, and that seems unlikely too. So I think we can discard these two possibilities. But there remains one more, which is that it could be that we simply don't understand how gravity works on these enormous scales. Gravity is incredibly well tested in the solar system, not necessarily well tested out here on much larger scales around galaxies. And if we want to get to the bottom of which of these two is more likely, the invisible exotic mass that we can't see, or some change in the law of gravity, we're going to need another kind of data, some other information beyond the rotation curves of galaxies. And their nature is kind, because it's given us other probes of dark matter. And I'm going to try and present another couple of them to you now in increasing levels of complexity. So the next key probe that we can use to go after dark matter is called gravitational lensing. And here we've got to move beyond Newton's gravity to Einstein's theory of gravity. And in Einstein's theory of gravity, massive objects curve space and time around them. And this can cause the paths of photons to be deflected. So in this cartoon here, imagine that we have, this is not to scale, obviously, because there's the Earth where we live. This is supposed to be a giant cluster of galaxies, an incredibly massive object that might have 10 to the 15 times the mass of the sun in some cases. And there's a bright distant galaxy or even brighter quasar. And now imagine that light from that source has to travel through the lens to reach us here on Earth. Now, if that happens, the light could come at us directly, and it would like to, of course, travel in a straight line like light does to us, but it has to move through the curved space around this galaxy cluster, so its trajectory is bent. And so to us on Earth, it looks like that photon of light came from over there. So we get an image of the original galaxy that's a bit distorted and displaced from its true location. But the photon of light can also come around the other way and produce a second image or more that's also distorted in a different part of the sky. So we can actually go out hunt for this effect by looking for multiple copies of the same galaxy distorted on the sky around massive objects like galaxy clusters. But the thing I find really cool about this is we call it lensing because actually mathematically it's very similar to optical lensing. There's a key conceptual difference because in an optical lens, the photon path is bent because the speed of light slows down. But here the photon path bends because the path length is a bit longer. But actually for thin lenses, the mathematical equations are very, very similar. So we're all familiar with optical lenses. There's a good old-fashioned biconvex lens you might have in a pair of glasses where you have an object and light shines through it and gives you a good old inverted image on the right. Now, of course, gravitational lenses are not going to work like this. It would be odd if nature created a giant cluster of galaxies that worked like a perfect biconvex lens. A gravitational lens might look a bit more like this. And if you shine light through that, you'll get multiple distorted, inverted images, just like I showed in my cartoon. Okay, so it's audience participation time. Can anyone think of a glass object that looks a little bit like this?
Wine glass.
A wine glass, brilliant, yes. So the resident alcoholic has found the glass first. And as luck would have it, I have dropped my stick. I have a wine glass here, right? And so I'm going to show you how you can make, startle all your friends at dinner parties and so on by making your very own wine glass lens. And all you need is a wine glass like this. I do recommend emptying it first, or your friends will be slightly less impressed. And then you need an extremely expensive prop like this one, a piece of paper with some circles on it. Now, in this example, this is going to be the gravitational lens, and this is going to be the distant source galaxy, okay? And we're going to try and shine light through the base of this wine glass and see if we can't produce this lensing effect. So if we can just switch over to the camera. There we go. Okay, so hopefully you can see this. Here's my expensive prop. You can also marvel at my artwork capabilities. Okay, so here, imagine this dot here on the top right, if I can get it right, there it is. And at the moment, it's far from the center of the lens, so you see it's still perfectly round. But as it approaches the lens, you can see this here, you see it here. As it approaches the lens, you see it starts to be bent into a sort of bean shape. And that's what we might call weak lensing. But as we get closer and closer, it gets more and more distorted, and you start to pick up these multiple images. And when it's right on axis, you get a perfect ring like this. And that's called an Einstein ring. So we go through off axis, it's round, bit bean shaped, starts to be curved, multiple images. And then as you get it really on axis, a perfect ring around the base of the wine glass like that, called an Einstein ring. Now the weak lensing, when it's slightly bean-shaped, it's very difficult to detect in an individual galaxy because some galaxies can be a bit distorted or flattened, but we can still detect it statistically by looking for the same distortion across many galaxies in the same patch of the sky. So we have two different ways to do lensing. You can either do it statistically by seeing many galaxies all bean-shaped in the same sort of way, or you can do it for an individual galaxy. If it gets close enough to being on axis to the lens, you actually see arcs and full circles. And the thing I find absolutely incredible is that what you can do here with this simple little wine glass, that effect you actually see in the real universe. So there's the wine glass, just in case it wasn't clear. And so here it is. This is a real gravitational cluster This is Abel 1703, everyone knows and loves. And in the middle there, you can see actually there's lots of features all around the whole image of different arcs from gravitational lensing. This is actually a lensing arc here of a background galaxy. There's some over here, and so on. But of course, the most spectacular one is right near the middle here, where you see an almost perfect Einstein ring formed by this background galaxy. And you can see, if you look carefully, 4 copies of the same galaxy here, 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 and here. And we can use these distorted images with software to try and reconstruct the mass distribution that must have produced those distorted images. Okay? And that's how we can use gravitational lensing to map out the gravitational field, to map out the distorted space-time, and then to try and make inferences about the nature of dark matter. Now, there are many, many examples of this, but probably the most famous, and the one that I want to focus on for this talk, is called the bullet cluster. Okay? And it should be called the bullet clusters, because it's actually 2 clusters. So a cluster, and I've already alluded to this before, is a gravitationally bound collection of many galaxies. It can be hundreds to thousands of galaxies all bound together, moving in one giant, what we call halo of dark matter. And what you're seeing in this picture, as I said before, is 2 clusters, and we think what's going on is that this small galaxy cluster over here, you can see by this blue blob, has recently passed through the larger galaxy cluster over here that you can see by this much, much larger blue blob. Okay? And this is a composite image, so you could... color code that's used for that? Yes, that's exactly where I'm going, thank you. The white stuff here, the white through yellow stuff here, these are the galaxies. This is an optical image, and you can see the clustering of galaxies here around this cluster, and then there's an extra clustering of galaxies around this cluster here. And then in blue is marked where the peak of the gravitational field is as measured from weak gravitational lensing. So you can see that the gravitational field is centered on this cluster of galaxies here and on the cluster of galaxies over there. But in red, I'm showing something quite different. In red, I'm showing X-ray emitting hot hydrogen gas. Now, it turns out that these galaxy clusters are so massive, so 10 to the 14, 10 to the 15 times the mass of the sun, that if you fill them up with hydrogen gas, that gas must be in the form of plasma. And it's so hot, 10 to the 7, 10 to the 8 Kelvin, that it emits photons in the X-ray. So you can't see this, of course, from Earth, but you can put a satellite in space, an X-ray satellite. You can study this system with your X-ray satellite, and if you build a false color image of the X-ray emission, you see this. Now, what's interesting is if you look at most galaxy clusters, the X-ray emission, of course, is centered on the galaxy cluster, as you'd expect. But that's not what we see here, because this system is not in equilibrium. It's just gone through this merger. And you see this beautiful cone of shocked gas coming off from the smaller of the 2 galaxy clusters, but even the hot hydrogen gas from this galaxy cluster has been displaced, and over time, as these 2 systems merge, the gas will fall back down into the center of the gravitational wells, and you will end up with one slightly larger galaxy cluster, but that hasn't happened yet. Now, why is this interesting? It's interesting because if you ask where is most of the mass in this system that I can see, it's actually in that hot X-ray emitting hydrogen gas. So most of the visible mass is actually shown in the red bits. But the gravitational mass, as measured by the curvature of space and time, is where the blue bits are. So if we want to explain this by changing the laws of gravity, we have to come up with a very, very strange theory. We have to come up with a theory where the gravitational field is physically displaced from the object producing it. It would be like you could see the sun, but the Earth was orbiting something else. Okay? And that's no one has yet managed to come up with a theory that will produce such behavior and that can actually fit these data. By contrast, if dark matter really is an invisible substance, then that substance can move, and it can move like the galaxies do. It's what we call a collisionless fluid. It just flows through itself without any effect, and you end up with the dark matter being over here and the dark matter being over there, and it matches this data perfectly. Now, that doesn't tell you precisely what dark matter is. It just tells you the way it behaves. It behaves like a ghost. It just passes through itself and only exerts its gravitational influence alone. Okay? Now, this is consistent with the idea that dark matter comprises some new fundamental particle of nature that we haven't yet found, but we're not quite sure if that's correct or not, but this does suggest that the idea that it's alternative gravity isn't quite right. Okay, so this is all well and good, but we would like to also have more information, more data to throw at this problem, because at the end of the day, it's still pretty crazy, the idea that the universe is filled with invisible stuff, and that invisible stuff is, there's a lot more of it than the stuff we're familiar with. So what else can we do? Well, the final probe I want to talk about is using the entire universe itself as a probe of dark matter, to try and use the structure of everything around us, from the smallest galaxies up to giant galaxy clusters, to ask, could that be there? Could we see the structure that we see in the universe today if we lived in a universe without dark matter at all? And this probe is probably the most challenging one to understand, but I know you're all with me on this, so we're going to give it a go. So this is the only slightly scary graph I'm going to show for the whole talk, but I am going to walk you through what it means. So this is a plot of the power spectrum of the universe, the amount of power on different scales. So it's telling you how much structure there is, how many big structures and how many small structures. And the small structure described over here, right, this is called a wave number, which is the inverse scale. So small things are over here and giant things are over here. And what you're seeing is data here from two different probes of that structure in the universe. On the left, these gray bands, these measurements, are coming from the cosmic microwave background radiation. That's what's shown in this image here. This is a true tour de force. This is beautiful data from the Planck satellite that's measured photons in the microwave spectrum of the sky everywhere you look. And we think that these photons are coming from what some people call the afterglow of the Big Bang. They're photons that came from when the universe was a mere 400,000 years old. So what happened, we think, in the Big Bang picture of how the whole universe formed is the universe started very hot, very small, very dense, and it was so hot and dense, this plasma, that light itself was constantly reabsorbed and couldn't escape. But as the universe expanded and cooled, at about 400,000 years old, those photons could escape and stream out across the whole universe. They cooled down with the later expansion of the universe, and we see them today in this microwave part of the spectrum. And one of the really remarkable things is if you take one of those old television sets that people had, if you remember what a television is, and you could connect it with an antenna on top, and you detune it and you get that white noise, a few % of that white noise is actually these photons, this afterglow of the Big Bang. Now, the amazing thing is there's structure in this image. You can see it. It looks like a speckled egg. And these little ripples here, these are ripples in part of about 1 part in 100,000. So very, very small little ripples, but they encode the structure of the universe when it was very, very young. They tell us that there was already little fluctuations in mass everywhere. And it's those little fluctuations that grow as the universe grew and got older, and they merge together and they form all the galaxies in structure that we see around us in the universe today. So we can take an image like this and we can use it to work out how much power there is in the universe on large scales, and that's how we get these gray bands here. And the errors are really big on these large scales, and the reason for that is because we only live in one universe. On the very largest scales, we only have very little data, the universe we can see. And that's fundamental. We're not going to be able to do better until someone can invent a way to visit another universe, if such a thing exists at all. But as you go to smaller scales, the error bars become exquisitely small. You can't even see them all the way down to here. But at this point, we can't use the cosmic microwave background radiation anymore to probe ever smaller scales. We need a different method, another probe. And so over here in green, we're using a different probe of structure in the universe. And this is a beautiful probe called the LymanAlpha Forest. And here's a little movie by Andrew Ponson that explains how this works. So what I want you to do is imagine that you have an extremely bright galaxy in the very distant universe. We call this a quasar. And you're following a photon of light from that quasar as it travels across the whole universe to reach us today. And on its journey, it passes through lots and lots of intervening gas. Most of this gas is not inside galaxies. It's just freely floating about. But every now and then, it might pass through a galaxy as well. But every time it passes through a gas cloud, a little bit of the light is absorbed. And you pick up this forest of absorption lines in the hydrogen spectrum. Now, the more gas, the more structure there is along the line of sight, the more lines there'll be, and the less structure, the less lines. So if there was nothing in the path of the photon from when it was emitted to us, there wouldn't be any lines, okay? So we can use that information, how many lines there are, how dense this thing is, to try and figure out how much structure there is in the universe. And this is a probe of much smaller scales than the cosmic microwave background radiation. So if we do that with a bit of modeling, we get these green data points. So now we have this beautiful data, it's all data, telling us the structure of the whole universe from very large scales to very small scales. And what we can then do is we can build a model of that universe that has different bits in it. It has hydrogen gas, it has maybe dark matter, maybe not. And we can ask, does that model fit the data? So let's start by trying to construct a universe that has no dark matter and ask, how well do we do? Well, we get something like this, the blue line. Yes?
What is the vertical axis?
This is just power. So it's just a measure of how much stuff there is at each inverse scale. So the normalization doesn't actually matter very much. It's really just a relative measure of how much stuff there is. So most of the structure in the universe is on a scale, an inverse scale of about 10 to the minus 2 megaparsecs. That's what this plot is telling you. There's less stuff bigger than that and a lot less stuff smaller than that. Okay? So we try to build this model with no dark matter and we get this blue line, and it goes spectacularly wrong. And it goes spectacularly wrong in two ways. So first of all, it's falling off far too quickly here. So on small scales, there just isn't enough structure. And secondly, you have these giant wiggles that are just not seen in the data. And those two things happen because this model has only hydrogen gas and photons of light. There's nothing else to put in it. Those are the only things we know about in the universe, and that's what we've put in. But the photons of light couple, they talk to the hydrogen gas, and the hydrogen gas has pressure and sound waves that travel through it. So the acoustic waves that travel through that hydrogen gas produce these wiggles, and this suppression is produced by the interaction between the gas and the light. So the only way to get around this problem is to introduce another component that doesn't interact with the photons and that doesn't have the sound waves, it doesn't have pressure. And that's exactly what dark matter does. It's a pressure-free fluid, no sound waves, no photon interaction, and if we put that into the model, then we get what we call the standard cosmological model, lambda-col dark matter, and we get a beautiful fit to the data. But I've pulled a slight fast one.
This data is coming from the light, right? Data coming.
The data is an interpretation of our understanding of the photons that we're seeing. So if we've misinterpreted what those photons mean, then yes, all bets are off. And that might be the way we have to go, because this model, much as it gives a beautiful fit to the data, is even more crazy. Because it tells us that not only do we need dark matter, 27% of the universe, we need a whopping 68% that's even more mysterious, this dark energy. And I could give a whole other talk on that. We really have no idea what this is. But this is what the model seemed to require. And a mere 5% is made up of familiar atomic mass. So we've gone from crazy to even more crazy, but that's the only way we can interpret these data at the moment. Now, of course, this is all fine, but we still don't know what dark matter is. I still haven't told you. So if we want to learn what dark matter is, we're still going to have to go further still. And luckily, we can. If we go back to here, this model fits the data, but already not every model does. So I can cook up a different model that fails also, like this one. This is called a warm dark matter model. Now, in this model, dark matter, when it decouples from the whole universe, is slightly relativistic. Just means it's a bit of a lighter particle, it's moving at faster speeds, and that causes structure formation to happen a bit later and to be suppressed on the smallest scales. And you see that sharp here as a cutoff in the power spectrum that clearly doesn't match the data. So we can already rule out this model, that dark matter can't be this warm. And we can push this model ever closer to the data and get a constraint on how warm it can or cannot be. And if we can push this comparison between theory and data much further over here to the right, then we can really start to tighten the screws on these different models, and we can start to make inferences about what dark matter might actually be. And that's the field of near-field cosmology, which is my own research area. Now, there's a challenge. As we go further over the right here, the structure formation starts to go what we call nonlinear. And that just means that the little lumps that are growing under gravity don't just grow alone under gravity, they start to merge with each other. And the only way we can understand that is with detailed simulations of the formation of the whole universe. Something like this. So this is from Volker Springel's group. It's called the Aquarius simulation. And this is a calculation of what the dark matter looks like over the whole history of the universe for a big blob of dark matter that would host a galaxy like our own Milky Way. And you're seeing in this movie the density of that dark matter fluid. These lumps here are high density, through to black and so on is very low density. And in this particular simulation, has modeled only the dark matter fluid. So there's actually no normal matter in this calculation at all, only dark matter. And it's assumed that the dark matter is cold, so perfectly non-relativistic, and it's assumed that it's collisionless, so completely pressure-free. And it forms these blobs that merge hierarchically to form ever larger structures. And many of you will have probably seen a movie or a picture of this kind of structure formation before. And we think that at the center of these blobs is where galaxies form. So gas would cool, stars will form, and these things will light up as visible galaxies in the real universe. Now, in a calculation like this, we can get lots and lots of information out that we can go and...
Without interaction, still form this concentration.
Yes.
It's counterintuitive, yeah?
It's just that it's collapsing under gravity.
Well, but still, the Earth collapses because there's also electromagnetic interaction. The Earth wouldn't be like that, right?
Ah, yes, so there's no... So the point is, in this calculation, dark matter has nothing to stop the collapse. So when it collapses, it's a bit like, you falling through the center... No, because it's like if you took an object and you dropped it through the center of the Earth, it would go through and then it just oscillates back and forth. Yes, exactly. That's right. So you can take out lots of information from a calculation like this that you can then go and compare to the real universe and try and work out what dark matter is, or at least what it isn't. Okay? So one thing I can do, I can count up all of these dark matter blobs. And if I just calculate the statistics of these blobs in some volume, I could then go and compare it to the number of actual galaxies that I can see. Okay? And that's called the halo mass function. This is directly probing how much power there is on very small scales. So this is probing the matter power spectrum that we showed before. So if I do something like this is going to give me a constraint on how warm dark matter is, for example. But I can now do something new, something I couldn't do before. I can look at the internal structure of dark matter inside one of these blobs. So I can actually calculate where inside a galaxy the dark matter should be. Near the middle, near the edge, somewhere in between. And that's what I'm showing in this graph here. This is the result of one of these simulations, and it's showing you the density of dark matter as a function of distance from the center. And the density is high in the middle and then falls off, but it falls off in a very characteristic way. And this profile has become so famous in the community that the three authors who wrote it, Navarro, Frank, and White, in 1996, is referred to as the NFW profile.
What's the x-axis?
This is the radius from the center of the galaxy. The units, sorry, I should have changed this to light years. This is kiloparsecs. If you multiply by 3, you get kilo light years, give or take. And this is... Yes, this is getting bigger and bigger and bigger and bigger this way, and this is getting bigger and bigger and bigger this way, and the density is falling off very steeply this way. Okay? And again, if I change the nature of dark matter, I change the model prediction. So a popular model that people are talking about at the moment is called self-interacting dark matter. So in this model, you add a new force that acts only in the dark sector, and that can do interesting things like turn this prediction into something much flatter. That's the self-interacting dark matter prediction, something flatter. So you could go out and measure where dark matter is inside galaxies and ask, does this model give a better fit to the data, or that one? Okay? Now, this all got very interesting, this counting of galaxies on the sky and this measuring of the dark matter distribution inside galaxies, because it's on these two probes, these two things, where that standard cosmological model started to fail. And scientists get excited when models fail, because our job is to break models, not to defend them. I mean, it's supposed to be anyway. So we should be spending all of our time thinking, what's the best way to destroy my pet theory? Okay, so when it fails, that's great. That's how we learn. That's how we're learning things, right? So everyone got very, very excited about this. Thousands of papers on these problems. So what was the problem? Well, the first thing is, you say, well, let's go out and try and measure where the dark matter is inside a galaxy and see if it matches that prediction from the calculation. So here's a galaxy. This is a nearby dwarf irregular galaxy called WLM. In red, this is hydrogen gas, and then you can see the starlight here in this composite image. And you can take this hydrogen gas and measure the rotation speed as a function of distance from the center, just like Vera Rubin did for M31. The key difference is now we're not trying to detect whether this thing has dark matter. We're trying to go a step further and measure exactly where the dark matter is inside this system. So here's another plot now. This is showing distance from the center of the galaxy, same units as before, versus the speed that it's spinning at. And this is the real data for WLM, rising up like that. But now we're going to fit to these data our specific model for where we think the dark matter should be. Now, there must be lots of dark matter in this system because this is what the gas and the stars contribute to the rotation, very little, but basically negligible. But here's the model. It fits out here at large radii, but at small radii, it fails completely. It's predicting lots more dark matter in the middle of this galaxy than the data want. If I turn that into an inference of the dark matter density, here's those cuspy models that I predicted. They're too steep, and the data wants something much flatter, like a core. Now, of course, this got very exciting because that's what the self-interacting dark matter model predicted. Maybe this is telling us that dark matter has a new force, a fifth force in the dark sector. Be a tremendous result, Nobel Prize-winning stuff, if it's correct. And we'll come back in a moment to whether it's really, we think that's the correct interpretation. The other problem is, as I said, you can count up the number of bound dark matter blobs and compare them to the number of halos that we actually see in the simulations and so on. So here's a schematic diagram of what's called our local group of galaxies. This is where we live in the Milky Way, and these are all the galaxies orbiting around us. These are called dwarf galaxies because they orbit around our one. And there's the Andromeda galaxy, a nearby companion that I showed you a picture of right at the start of the talk. And those are all of its little companions orbiting around. Now, we find new galaxies every single day orbiting these two systems. It's a very exciting and fast-moving field. But even with all of the new discoveries and all the new satellites that we found, they're still far smaller than the number of bound dark matter blobs that the theory predicted. So here's an example of a calculation now with two galaxies to match Andromeda and Milky Way. But you can see all of these bound dark matter blobs here, hundreds or thousands of them. If every single one of those blobs lights up in stars, then the theory doesn't work because there just aren't that many dwarf galaxies. So that's called the missing satellite problem. Where are they? Why are they not there? Excuse me. So that's all well and good, but if you were paying careful attention, you'll realize that all of the predictions I talked about, this steep cusp dark matter profile, the number of satellites and so on, were for a simulation that had only dark matter. It didn't have any normal matter in it. So I haven't actually been comparing apples with apples, I've been comparing apples with oranges. I'm comparing a calculation of a universe that we don't actually live in to the real universe. I mean, if we lived in a universe with only dark matter, I wouldn't be here giving this talk, right? I've left out the one bit that we know is real. So that does beg the question, if I put the real stuff back in, will it materially change those predictions? Could it solve these two problems? Well, for the missing satellite problem, you could imagine it might, because we don't know which of these dark matter halos light up with stars, and I could concoct some sort of reason why some are bright and some are not, and I could fiddle about with how galaxies form and find some sort of solution, and there are many, many papers doing exactly this. So you can come up with plausible ways of solving this problem by simply positing that many of these dark matter blobs are simply very faint or invisible. But the cusp core problem is much harder. It's much harder because it seems to be telling us that there's actually less dark matter in the middle of galaxies like WLM than the model predicted. I can't solve that by just painting some stars on some galaxies and not on others. I have to physically move the dark matter from the center of the galaxy out. And the dark matter interacts only via gravity, which is an incredibly weak force. If you want to have some idea of just how weak gravity is, the entire Earth is keeping my feet on the ground, and a few atoms in the floor are stopping me from falling through it. So gravity is very, very weak. So how is gravity going to do anything? Surely it's not important. Surely the problem stands. What I'm going to try and convince you of is, in fact, there is a way in which normal mass can actually push dark matter around inside galaxies, and that this can actually solve this cusp core problem. And then I'm going to show you evidence, observational evidence, that this may in fact be the correct interpretation. So we call this idea dark matter heating, but I put heating in quotes because, remember, dark matter doesn't have pressure, it doesn't have temperature, it's this collisionless, ghostly fluid. So when we talk about heating, it's not in the sense that you might imagine. What we really mean is you imagine a little dark matter particle orbiting inside a galaxy. We're just going to try and raise the energy. We're just going to try and push it further out inside that galaxy. And that's what we mean by heating. Now, how on earth would this actually happen? Well, it turns out that in these tiny little dwarf galaxies, which is where the cusp core problem rears its ugly head, I've done it again. These little dwarf galaxies are very, very interesting, rich physical laboratories for understanding how galaxies form. So here's a beautiful picture of one. This is called the M82 galaxy. And you can see that it doesn't look anything like the last galaxy we looked at. You can see there's a nice galaxy here in the middle, but look at all this stuff. There's a huge wind being blasted off from this galaxy. And this is all real data. It's a real system. It's a lovely system. And we think we understand what's going on here. Right? The gas cools by emitting light, and it condenses down into the galaxy and forms some stars. And then at the end of their lives, some of those stars explode. And they return lots of energy and metals and momentum to the surrounding gas, and they push it out, and they drive a galactic-wide wind. So we know observationally that in these tiny little dwarf galaxies, gas is constantly flowing in and being pushed out, and flowing in and being pushed out. And it's happening over and over and over again throughout the lifetime of that galaxy. So if that happens, if gas is constantly flowing in and being blasted out, then the gravitational potential, the gravitational force in the middle of the galaxy will fluctuate with time. Now, if I took the sun and I fluctuated its mass up and down, even by a few percent, continuously every year, then the Earth and all the other planets would slowly be pushed out. They'd slowly migrate out of the solar system. So don't worry, I'm not going to do that. You're all safe. But we think that these dwarf galaxies could actually do that. And let me just show you a really simple toy calculation, a little movie showing how this works. So I want you to imagine that this is one dark matter particle, not to scale, big red blob, and it's going to be moving on a nice circular orbit inside a galaxy, minding its own business, nothing to see here. And then, at some point, after about 1 billion years, I'm going to introduce a fluctuating gravitational potential. And we see what it does to the orbit. So there's the orbit going around nicely, nice circular orbit, nothing going on over here. And then around about 1 billion years, I introduce this fluctuations. These are about 10-20% fluctuations. And you see the orbit changing, migrating outwards. That's why I said it would be bad news for the Earth if we did this to the sun, because that would be the Earth, and it would get cold, and that would be not good. It might even hit one of the other planets. Okay? So this isn't going to happen in the solar system, of course, but in dwarf galaxies where gas is flowing in and out, this could happen very, very naturally. And it's flowing out because of supernovas, and it's flowing in.
Enough for one supernova has such effect on the level of galaxy?
No, not one supernova. There's a whole galaxy-wide starburst. So yes, exactly. So you have many supernovae going off, and they add together to drive these winds. Exactly. So here's a more sophisticated calculation of that. What I'm trying to do now is model a dwarf galaxy. I've now got, there's dark matter in the calculation that I'm not showing, but here you're just seeing the gas density viewed from above, and we're going to allow that gas to cool and form stars, and at the end of their lives, the stars can explode. And so you see there is a big rotating disk, roughly, but it's also quite violent. And whenever the stars form and explode, they drive these big holes in the interstellar medium, they drive gas out again, and this thing does naturally drive a wind, rather like the one you saw in M82. So in a simulation like this, gas is constantly flowing in and out, but now we're resolving those physics. We put all those physics into our calculation. And what happens at the end of a calculation like that is that the dark matter is, in fact, heated up. It starts out really dense like this, and then over time, it gradually migrates outwards, and the dark matter density, this is showing the dark matter density here as a function of distance from the center, starts out really dense, and then after 14 billion years, takes a very long time, the density slowly comes down and down and down and down until, look, it's almost a perfect core. And that just happens naturally in the calculation. But we can go further. We can now go back to the data and ask, well, does this solve the problem? Does it actually fit the data for WLM? So there's our WLM galaxy. There's our cusp core problem. It doesn't fit the data. It's a disaster. We switch on our gas, our star formation, our stellar feedback. We get a new prediction. And this is now the new fit. And this is with no more free fitting parameters, right? Everything is tied down by the calculation. There's no more free parameters. But the fit is now extremely good. And it works for WLM, but also for all the other dwarf galaxies that we've looked at so far. Now, this is encouraging, but I can see there's some holdouts in the audience. Because this problem dates back to 1994, not long after my last trip to New York. And so it's a very old problem. And so I've solved an old problem that we already knew how to solve in a way. We knew that if you put a core in, it would solve this problem. My calculation put a core in, and now the problem is solved. So maybe I'm pulling a fast one. The mark of a good theory is not that it fits all the data you already have, but that it makes a prediction, and that you can go and test the prediction, and you can see if the prediction turns out to be true or false. So over the last couple of years, we've been working hard to see what does this model predict that's different? What can we go out and test? And does it actually work? And the good news is there is a prediction, and we can go out and test it. So what's the prediction? Well, if you remember, in order to get that dark matter to heat up and be pushed out, I've got to wiggle the gravitational potential up and down over and over and over and over again. Now, in a galaxy like WLM, we know we can measure the star formation history of this galaxy. We can use the stars that we see in it today. We can do a kind of galactic archaeology. We can dig through the colors and properties of those stars. We can figure out how long it's been forming stars. That's a remarkable field in its own right. But it means we know that it's been forming stars basically continuously forever. So it's had all the time it could possibly have to push that dark matter out. But this isn't true for every galaxy. Here's a different galaxy, Fornax. This galaxy orbits close to the Milky Way, and it's come a bit too close. About 1 to 2 billion years ago, we think, it came too close to the Milky Way, and it lost all its gas. No gas in Fornax at all, as best we can tell. It got too close to our galaxy, and our galaxy robbed it of all of its gas. And when it was robbed of all of its gas, it was robbed of all of its fuel to form new stars. So the star formation stopped about 2 billion years ago. But 2 billion years is no great shakes in the history of the whole universe. The universe seems to be 14 billion years old, so it still had 12 billion years of star formation. Plenty of time to push its dark matter out. But now look at this little galaxy, Draco. This galaxy is so faint, you can't even really see it in this picture. It's not these red stars. These are unfortunate foreground stars. It's a faint, fuzzy blob that was actually first seen on a photographic plate, which I think is a testament to the power of the human eye. We now do these things using more sophisticated digital search techniques, but believe me, there is a galaxy there. It has barely a few 100,000 times the mass of the sun in stars. A very, very small thing indeed. So in comparison, our galaxy has maybe 100 billion stars. This thing, a couple 100,000. Very, very small. And the reason it's got so few stars is because it fell into the Milky Way much, much earlier, about 10 billion years ago. So it formed stars for about 2 billion years, and then it was snuffed out, lost all its gas, just like Fornax. But that means it didn't have as long to wiggle its gravitational potential up and down as Fornax or WLM. So our theory makes a prediction. If we have less and less and less star formation as we move from WLM to Fornax to Draco, we wiggle that potential less and less and less, and if the theory's right, we should start to get ever steeper dark matter. The dark matter density should be higher and higher and higher for less and less and less star formation. And that isn't true if I change the nature of dark matter. If I fiddle with what dark matter is, it'll affect all three of these galaxies, because it doesn't care about star formation. I'm just going to change the nature of dark matter. So it's a testable and distinct prediction.
When it says like a gas, it's smaller influence on dark matter.
Yes.
It must be opposite because all gravitational energy comes from explosion. Who cares about gas? They only transmit the energy. Gravitational energy comes from explosion.
Oh, yes. So the fact that the galaxy doesn't have gas is just the reason why the star formation shut down.
Okay.
But the key point is how long did the stars form for? And in this galaxy, there was only 2 billion years of star formation, and in this one, there was 14 billion years
So
of star
it's not so much
formation.
gas, but how many explosion were there, right? This was big.
Oh, right, yeah, okay, so that's true. So these galaxies have been chosen so that for the time that they were forming stars, they had a similar star formation rate, so a similar number of explosions for that time. But you're right, less explosions here, many more explosions there. Good. Questions are good, by the way, because it means I know that you're paying attention. This is the last little thing to show you, and then we'll switch over to questions. So let me just show you then the results of this study. Okay, we studied about 18 galaxies, but I'm not going to show you 18 galaxies because you will probably storm the stage and carry me out of here. So I'll just show you 3 or 4 to illustrate the idea. Okay, so here's WLM again. You've seen this one already, but now what I'm showing you on the left here is its star formation history. So this is the beginning of the universe, the Big Bang, and this is today. And this is the rate at which it's forming stars, so the number of solar masses per year. And you can see that within the error bars, it's had a roughly continuous star formation from the Big Bang all the way through to today. And then over on the right here, this is our measurement of its dark matter density. And you can see it's very flat and core-like over a wide range of radii. Now let's look at Fornax. You remember the one that shut down its star formation a couple of billion years ago? Here you see it. Right, there's the star formation going along, and then whoop, it drops off, presumably because it fell into the Milky Way. And you can see it's a little bit denser than WLM, but not statistically significantly. So I wouldn't claim that it's denser than WLM. It's not within the error bars, but it's a little bit denser. But now look at Sculptor. This is a galaxy whose star formation shut down somewhere between 6 and 10 billion years ago, and you can see that it's systematically denser. And now finally here's Draco, the one that shut down very long ago. There's its star formation history, a couple of billion years of star formation, and then that's it. And you can see how much denser it is than Fornax. Lots more dark matter in the middle. And to guide the eye, there's a flat core, there's a steep cusp. So Draco seems to have this central dark matter cusp that the original models predicted. The things that don't are the things that form lots of stars. Okay? So if this is right, then it does solve this problem, this cusp core problem for dwarf galaxies. It does suggest that our standard guess about what dark matter is, being this pressure-free, collisionless fluid, at least for the time being, lives for another day. But the really fun thing, I think, is it implies that dark matter can be physically moved in the center of galaxies as galaxies form. And that suggests that whatever dark matter is, it must actually be some stuff, some real substance. So this is rather like the bullet cluster result, but on very much smaller scales, suggesting that dark matter really is a substance, and we simply just have to get out there and find out exactly what it is. So at that point, I come to the main conclusions. I have sort of 3 take-home messages. The first one is there's a very vast array of data, huge amounts of data out there, that suggests that the universe is filled with this mysterious, invisible dark matter substance. We see it in the rotation curves of galaxies, so how fast they're spinning. We see it from gravitational lensing, and we can see it in the structure in the universe on all scales, from the tiniest things up to the very biggest. We want to go further, though. We want to find out what dark matter actually is, so we started to study its distribution inside dwarf galaxies. And there we've uncovered evidence, I believe, that dark matter can actually be heated up, kinematically heated up, and moved around by gas inflows and outflows in these tiny dwarf galaxies. And if that's true, it suggests that dark matter is some sort of substance, and it's consistent with the idea that dark matter is probably a weakly interacting massive particle that remains to be found. And
When you say massive, you mean it has mass?
I mean, it has mass, exactly, yes. That's right, yes. Not, well, it could have quite a lot of mass, but yes, sort of proton mass or thereabouts. Now, that may sound weird, like, a new particle that we haven't found. Do we really believe that? Well, the fact is there is already 3 dark matter particles that fit the bill that we already know about. and those are the neutrinos. There's an electron neutrino, a muon neutrino, and a tau neutrino. And these particles are so weakly interacting that if you wanted to stop one from entering this room, you'd need about a light year's worth of lead. And even then, it would only be 50-50. So we know that there are particles already that we have found that are incredibly weakly interacting, that do still have mass, but neutrinos can't be the dark matter because they're too light. They have a mass of about 1 electron volt or thereabouts. In fact, the mass is so low we haven't been able to measure it yet, but we know it's not zero. But when it's that low, it means that they travel at almost the speed of light. And if they're traveling at the speed of light, they cannot remain gravitationally bound to galaxies, and they just drift off into the universe. So neutrinos, they have much of the properties we need, but not all of them. But if I could find a particle like a neutrino, just a bit heavier, then I would have the perfect dark matter candidate. And everything I've shown you today would be perfectly consistent with that idea. So the race is really now on to see if we can find such a particle, characterize it, and if we can, then I think it would be a crowning success of these kinds of gravitational probes of dark matter that would suggest that we really did get it right and we were on the right lines. So I'll call it a day there, and thank you for your attention.